we will welcome Professor Fabio Sciarrino from Sapienza Università di Roma in Italy, and the title of his talk is Machine Learning for Photonics Quantum Information Processing. Hi, Fabio.
Hi to everyone. Good morning, Pascal. It's a pleasure being here.
It's a pleasure for us too. The screen is yours.
Thanks, Pascal. So, first of all, thank you for the kind invitation. So today I would like to show you the work that I've been carrying out in the last few years, which address the interface between machine learning and photonics quantum information processing. So in this framework, our goal is to exploit classical machine learning to obtain new insights into quantum physics and for quantum engineering. So the principle is that you have a device, which is quantum. This device is generating data. And the goal of the machine learning approach is to certify, identify, classify the underlying structure of the quantum system. So I repeat, in this scenario, the data are generated via quantum hardware, and then you feed this data inside some classical machine learning methodologies. You can have a variety of different approaches, and the final goal is to somehow boost your capability to characterize and handle a quantum hardware. We have been working in this direction in different subfields. To validate quantum photonics platform, I will focus first on that topic. Then we consider how to extract information for quantum metrology, which corresponds to phase estimation. Then you can have other interesting applications to classify quantum state of light, to learn quantum state, and to infer quantum causal structure. I won't have time to also address the last 3 points. I will focus on the first 2. So the first framework is how to validate quantum photonics platform. So let me very briefly introduce the framework. The framework is how to achieve quantum supremacy. We are all now familiar with the concept of quantum supremacy, which identifies controlled quantum systems which are able to overcome classical one for a specific given computational task. This concept was introduced by John Preskill a few years ago, and has received a lot of attention in the last years. In particular, I would like to exploit this review of 2018 on quantum computational supremacy, which highlights how this concept is so fundamental because it represents a key milestone towards the development of the ultimate universal quantum computer. Several approaches have been undertaken to challenge the quantum supremacy achievement. Some use superconducting devices. Clearly today I'm going to focus on the photonics hardware. So what is the idea? The idea to achieve quantum supremacy using photons exploits the concept of boson sampling. What is boson sampling? Is n bosons, in our case photons, which propagate over an array of m optical modes which are largely interconnected. And then the goal is to have the photons evolve in these m optical modes, and your target is to sample from the output distribution. Then you can have 2 fundamental questions. May I address this task with a classical hardware, and how it is complex to do boson sampling with a classical simulator? And then may I perform this with a quantum hardware? If you try to adopt a classical approach, the answer is that it is very difficult to efficiently simulate the distribution of the output mode numbers. And the reason is that the complexity is increasing exponentially. Then what you can do, you can move to a quantum hardware, you take n photons, you inject the model in an array of m optical modes, and you sample from the output state. So let me present to the concept of boson sampling via this simple presentation, and the goal is to really provide you an intuition of what's going on experimentally. The first step is to generate single photon. In our case, we use parameter conversion, but in the previous talk, you had a very beautiful overview on all the possible platform and the different technology. In our case, we generate two pair of photons. We have 4 photons. In the video, the yellow ball, you detect one yellow ball on one photon here. This is the trigger detector, and you are left with 3 photons. You inject these 3 photons into a single mode fiber. You synchronize the 3 photons in order to have indistinguishable single photon states. You have some delay line because we have very short pulses. You synchronize the 3 photons, then go in the single mode fiber, and then you are ready to inject the core of the Boson sampling experiment, which is where you implement the unitary transformation, which represents the evolution of the Boson sampling. How we can implement this? We have an array of interconnected beam splitter and phase shifter, and this array is realized in integrated chip. You see now the photons which evolve, there is a superposition principle, light will interfere along different paths. You will also have bosonic quantum interference, and that's the output. You have now an array of single mode fiber which are connected with single photon detector. You then have all these single photon detector. You measure all the different events as shown now. You will detect 1 and 0 photons. You will detect all the possible coincidence pattern in the output, and you will then register this coincidence pattern on your computer. This is a sampling. It's a sampling because you measure the output, and then you are sampling from an output state distribution. And what you get in your computer at the end is the string of 1 and 0. In this case, you have an animation which reports 3 photons over 13 modes. You repeat the experiment many times, and Boson sampling is over. This was an animation. If you go now in the lab, this is how looks our integrated chip. You see it's in the center, it's connected with some fiber array in the input and in the output. And as shown in the animation on the bottom left, these chips are fabricated via femtosecond laser winding. In the animation, you see a chip which is static in the sense that once it's fabricated, you have a fixed transformation. But then you can engineer your device. You can see in the picture some wiring because you have some thermo-optic controller which allows you to hit locally the waveguides. By hitting locally the waveguide, you can change the phase, you can change the transformation, and then you can change the transformation from which you are sampling. So that's a big picture of Boson sampling. And then these are some old results from our group, which are a small instance of Boson sampling. 3 photons which propagate over 7 modes, 9 modes, 13 modes. When you have 3 photons over 13 modes, your Hilbert space is pretty small. The Hilbert space dimension is something like 300. This means that as you see in the picture, you can detect all the events, you can measure the probability of each output state, and you can compare what you measure with the theoretical prediction, which is a classical simulation. If there is no quantum supremacy, you can characterize the output state, you can have the full control. But somehow this picture of Boson sampling is somehow not the correct one, because this is a small case scenario, and you are interested to achieve quantum supremacy to largely extend the number of modes and the number of photons. And in this slide, you can see how Boson sampling evolved from the proposal in 2011 to the first experiment in 2013 and to much more advanced experiments. You had, at the beginning, everything was static, then Bristol used the configurable circuits. We implemented in Rome other variants of Boson sampling, such as scattershot Boson sampling, and you have also a different way to generate single photon. You can see down on the right down side this apparatus which was adopted by John Wepan's group, which adopted single photon generated via quantum dot, and this allowed to largely increase the number of adopted photons. The same approach was also adopted by our chair, Pascal Senelard, in collaboration with Andrew White. So you see a large effort which allowed to increase the complexity of Boson sampling, more photons, more modes. If we now go to the last year, 2019-2020, there was this impressive paper reported in PRL with 20 input photons which propagate over a 60-mode interferometer. And on the right side, you can see how this last work really enlarged the dimension of the hyperspace, achieving a value of the hyperspace dimension, which is something like 10 to the 14, to be compared to the paper I mentioned before of 2014 with an hyperspace of only 300. So you see that the system is increasing in terms of complexity and so on. What we are currently working experimentally in Rome, in collaboration with Politecnico di Milano CNR, with the group of Roberto Zalame, is to have reconfigurable circuit as shown, where you can change the transformation, so it's not static. You can have a kind of universal Boson sampler device, and on the right side, also using some kind of two-dimensionality, which allows to increase the number of modes and to also somehow simplify how to achieve all the possible interconnection. But now the following question is, where is machine learning here? The point is the following. Once you have this huge hyperspace with dimension 10 to the 14, you will never be able to measure all the probabilities. Maybe you will carry out a sampling of 1 million samples. So you are really detecting a very small number of events compared to this huge dimensionality that you have in the labs. And the same arguments also apply to the Google experiment, where also the number of events which were sampled were much smaller than the overall hyperspace. And now we go to the following question. How can you validate a Boson sampling device? So how can you know that your device is really behaving as you expect, since you are not able to fully characterize the output state? And one can recast this point as the issue of certifying your quantum technology. So Boson sampling is a problem which is hard with a classical computer, but it's also hard to validate, certify the output. And the need to appropriate certification tools not only applies to quantum supremacy experiments, but also to quantum simulation. You then need to develop different methodologies to validate, certify the output state of your device. This is a subject on which I've been working not only half since now 2 years, and we adopted two kinds of approach. First of all, you have a kind of hierarchy of tests, and each test provides you stronger and stronger evidence that indeed everything is going as expected. You can then combine two pictures. One is more a physical approach, where you try to find out some very specific transformation which allows you to have some strong certification that you are indeed observing the interference of all the particles which are propagating. Here's the goal is really to have a kind of quantum certification of the genuine quantum behavior of your device. And the final goal is to have a stringent assessment on your device. On the other side, you can have a computational approach. Your device is generating data, and here you want to use a variety of machine learning techniques, from the more simple, like Bayesian inference, to more sophisticated one, which exploit pattern classification, neural network, and so on. And the key point is that you have a huge hyperspace, a small sparse set of data, and you want to take the maximum benefit from this data. The first goal that one may address is the following. Imagine you have a Boson sampling device, you have an alternative sampler that is based on the classical simulation techniques, and you would like to benchmark your Boson sampling versus some trusted Boson sampler or some other faked measured distribution. So I'm an agent, I will take the data from this unknown device, and I want to see if I can find a compatibility between this device, a trusted Boson sampler, or some faked distribution. And here, I repeat, the key point is that your sample of data is very reduced. So we carried out this work recently where we adopted some technique inspired by pattern recognition. So you have two samples of data, which is sample 1 and sample 2. Sample 1 is the one coming from your device. Sample 2 comes from a trusted Boson sampler or from a fake device, and you will have to check the compatibility between the two samples. And in order to perform this, we do some clustering of the data. And the space is huge, so you need to clusterize the data. Otherwise, you only have some small events in this huge dimensionality. You can create some bubble, you can have some clustering, you can have some chi-square test. And interestingly, these techniques works in very properly. In summary, you are able to discriminate if you are compatible with data which are generated via indistinguishable or distinguishable particles. And to this purpose, you use clustering. And what you can see here is a kind of two-dimensional pictorial representation of the Fock state in the n-dimensional hyperspace. Why is this technique working? And this is the result. So we tested experimental data, but since our data were generated via a small-scale device, we also generated data via a classical simulator for a number of particles up to 100, sorry, for a number of particles up to 18, over a number of modes up to 225. And this technique was working in those scenarios. The reason why it was working in Boson sampling, there is some kind of correlation between the output state, which allows the techniques to be successful. Then we also carried out some following steps, in which now I cannot focus so much, where the idea is to have some, we would like to have a technique that do not require so much training, but from the correlation of the data is able to tell you if the data are generated via distinguishable or indistinguishable particles. And to this purpose, we adopted two ingredients. First, the T-distributed stochastic neighbor embedding, which is an approach which allows you to visualize data sets of large dimensionality over a space of only dimension 2. So somehow you are compressing your dimensionality. You take few data from the experiment, you move the data from this huge dimensionality to two-dimensionality, then you get different pictures that you may see now in these slides. These slides were generated from different random unitary evolution, different kind of particles. You see that now you get different figures, then you use this figure to train a neural network where you give a label on whether the training data were coming from distinguishable or indistinguishable particle, and then you can apply this for new data and see that indeed now your methodology is able to understand whether your particles are indeed distinguishable or indistinguishable. So this concludes my first part on how you can use machine learning for certifying Boson sampling experiment. I will be very short on the second part, and here the goal is to extract information for quantum metrology phase estimation. We have carried out several work in this framework, and we have the following scenario. You want to carry out quantum metrology applications, such as imaging of biological samples, quantum microscopy. We know that in this scenario, quantum resources allows you to decrease the uncertainty in your measurement, and then to enhance the sensitivity for estimating unknown physical parameters. But our goal is to focus on the scenario in which you have a very reduced number of measurements. So you have a sample, you want to estimate the phase, but you use a very small number of photons that you send in your interferometer. And then the goal is to find an approach which allows you to optimize the way you extract information from this very reduced amount of data in order to obtain an optimal estimation. We know that when the number of measurements is large, we can converge to the appropriate limit. But the question is how you can do when you have maybe only 10, 50 photons sampling your unknown parameter. And for this purpose, we combine machine learning and adaptive phase estimation. The first work that we carried out were adopting only the estimation of a single parameter. You have a Mach-Lambda interferometer, you want to measure a phase, which is unknown, you want to do this only sending 10, 15, 20 probes, and we adopt different methodologies, particle swarm optimization, Gaussian optimal, particle guess heuristic, and more recently, in the last few months, the genetic approach. And then we found what was the best approach, also depending from the noise condition. This was, I will call it the entry level. And then the following level is, okay, now we would like to go to a multi-parameter quantum metrology. You want to estimate many parameters together. You have so different phases. You want to carry out simultaneous estimation of more parameters. And then you want also to do this in noisy conditions, so you prepare some state, you interact with the non-parameter, you carry out some measurement, you have some results, and you would like to have now the appropriate estimator in order to have the best estimation on the non-parameters. This research topic has attracted a great theoretical interest in the last few years, but very few experiments. To address this experiment, we also adopted an integrated interferometer where you have the 3-mode interferometer. You don't have now, it's an interferometer, you don't have beam splitter, you have a tweeter in the input, a tweeter in the output, and then the goal is how you can estimate the phase of the different arms. So we first developed this device to have a very good control on all the different features of the device. And then we started to implement different scenarios to optimally extract information. This is our last paper, which is currently impressed with NPJ quantum information, where we use a kind of Bayesian learning for adaptive multiphase estimation. And by adapting additional control phase shift, we could implement these multiphase estimation protocols in order to minimize the Bayesian expected variance. This only to allow to some, and all these results now multi-parameter need to be extended to more complex scenario where you further increase the number of parameters and where you will have to then exploit different methodologies in order always to get the best estimator on your system. And we're close to the end. So these are now the ongoing experiment in Rome. We are working on hybrid system based on quantum walk approach. Up to now, I introduced you how to use machine learning to certify, characterize quantum hardware, but we would like also to carry out machine learning in the quantum regime. And more recently, we are also focusing on how to exploit causal inference in complex quantum networks. I would like to acknowledge also supporting agency which supported this work, and also all the collaborators of my team. So thank you so much for your attention.
Thank you, Fabio. Thank you so much for this beautiful talk. Some questions, maybe. I will start. The first one is I want to acknowledge that you were one of the first to introduce this idea of using machine learning for this quantum optical technologies, which is, I think, a very important ingredient. You presented many applications for physics application. I want to ask questions about more pragmatic stuff. Like, I understood that also for defining a circuit corresponding to a quantum algorithm, it's also a complex problem. And I wonder how much of machine learning could be used in this area.
So, Pascal, thank you so much for the question. Maybe I would like to may share 2 extra slides.
Sure.
So, more recently, that's exactly in the direction you asked. Again, in a simple case, it's the problem of how you can calibrate a circuit. And that's a critical point, because as soon as you increase the number of parameters, this is becoming the complexity of the calibration is increasing very quickly. Also because typically when you have an integrated device, for instance, you may have different crosstalk between different parameters that you would like to control. So having the capability to properly calibrate your device in noisy condition, it's a critical point. So we recently carried out a couple of work in this scenario. Again, we started with a first calibration of a single parameter, and then recently we have extended it to multiparameter. Still, we are in a still simple configuration, but we're setting this multiparameter calibration currently to more complex device, and this is very promising. I guess this is an approach which is also has been adopted for the other quantum hardware, but you need, as soon as your complexity is increasing, having the capability to properly handle the system, it's a fundamental point. I would add a comment that when you have a device like a photonic circuit, what you can do this multi-parameter calibration with machine learning, sending classical light in the input. So this means that you can calibrate your circuit with these techniques with a very high signal. You use this calibration, this training, and then you move into quantum regime with a very strong same calibration on your device. I hope to have addressed properly your question.
You have addressed my question perfectly. Actually, the other thought I had was about the kind of the compilation part, of quantum computing. Like you want to implement an Hamiltonian if you want to do quantum simulation, and you need to transfer that to a circuit, a photonic circuit. Have you also thought about using machine learning here?
That's the second step that we are still working on that, which is more, I will call it, in the domain of quantum engineering. What I've shown you here is more really technological. It's really only how to characterize your device. And we call that the first step. The following step is the one that you were mentioning. You're perfectly right. Also, maybe your device is fully characterized. Then you need to have some kind of quantum engineering depending on your goal. It's something which is of interest, but we still have to work on that, at least in Rome.
So I have one last question. I hope it's not too naive, but the validation technique that you have developed is still, I think, for discrete variable Boson sampling. It's not applied to Gaussian Boson sampling yet. Can it be applied to Gaussian Boson sampling too?
So that's a big question. So what we did in the past, we extended it to the scatter shot Boson sampling, which is a specific case of Gaussian Boson sampling. It's not a generic case of Gaussian Boson sampling. Whether you can apply it in the mod or general scenario, it's a very good question, and I'm not able to provide you a complete answer. There are some work on that from other groups, but let me stress again, we don't have a final certification. What we are proposing you is only a way to provide you stronger evidence that everything is going as expected.
Yes.
But I don't have an answer for a general Gaussian Boson sampling approach.
Okay. So I think this is, thank you so much for your presentation and your very clear responses. I think we've reached the end of the session. I hope I'm sure you enjoyed it. We had amazing talks. So thank you all. And I guess the conference will continue a bit later. Thank you.